curvilinear motion. So for the last section, we use normal components and tangential components. Sometimes it's helpful to use polar and cylindrical coordinates. So this uses, they call it just cylindrical. It's really kind of a combination of cylindrical and polar. They're really almost the same. Now for this, sometimes we do have, for velocities, sometimes for this, we will have like a velocity in the theta direction and maybe a velocity in the radial direction. Whereas like it just, as I mentioned, just the last section, we only had tangential velocity, but here things might be moving in the radial or theta direction. And the same thing with acceleration. We might have it in the theta direction, which means going in a circle basically, or in the radial. So the main idea is you have kind of a fixed origin. So a fixed point from which you're measuring this stuff, and you could be going around that point, radial around, circular around the point, or you could be going in and out like along a radius from that point. And we'll have to go back a little bit to implicit differentiation. So the equations we're going to use will be VR, which is equal to R dot, V theta, which is equal to R theta dot. That's going to be like the radial acceleration, just simply going to be whatever the velocity, however it's changing, however the radius is changing, way to think of it. And V of theta would be the radius times how it's going to change in the circular way. And you'll see when we do problems, it'll kind of be a little bit clearer how we're going to use these. A theta is R theta double dot plus 2, like that. And then sometimes we'll also need, not always, we also move in 3 dimensions, and sometimes we'll move in the z direction. And so in those cases, we also need the velocity z, which is just going to be z dot, and a of z, which is going to be z double dot. Next, we're going to take a look at this problem here, 12-157. 12-157, a particle moves along a path defined by polar coordinates r equals e to the t and theta equals 8t squared radians, where t is in seconds. Determine the components of its velocity and acceleration when t is 1 second. Let's write this down. E to the t. Theta is 8t squared. And we're gonna need the derivatives, so we can just go ahead and take them. Now, one thing that's, remember, the dots, like R dot is the derivative with respect to time. So we don't have to do implicit differentiation because these functions are given as functions of time. So we just do the regular derivative. And of course, that's just gonna be E of t, R double dot is gonna be 2ET. And then over here, just do regular derivative. Theta dot is going to be 16t. Theta double dot is 16. And then just use those equations that we had just a second ago. And I'll write them down here, but just we're just going to use these. So let me write down, let me start with this one. So it just says V of R is going to be equal to R dot according to our equation sheet. And then we just, let's see, we want to know, let me just read that again. We want to know what's going to happen when T is equal to 1. So R dot is going to simply be this up here. And then just put 1 in. If you put that in your calculator, you get like 5.44 feet per second. And V theta, according to our equations, is going to be R theta dot. Once again, you don't have to memorize those. And let's see. And so we're going to need what R is. So R was 2e to the first. So I just put in what R was here. Then theta dot was 16 times 1. So I was just R from up here by put in T equal 1. And we put that in your calculator, you get around 87 feet per second. And then we need AR. Excuse me, yeah, sorry, I don't know. This looks like an N over here. This, when I wrote this down before, that should be an AR, by the way. AR. So AR is going to be R dot minus R theta dot squared. And R dot just from up above here. And R just from up above. I'm sorry. That should be 2e to the first minus 2e to the first. So that was R dot and R, which are actually the same. And then we have our theta dot 16 times 1, that's squared. Just move that up a little bit. And let me just be sure that all looks right. And when I put that in my calculator before, that was minus 1386.3 feet per second squared. Then A theta was R theta double dot plus 2 R dot theta dot. And that's just going to be 2e to the first times 16 plus 2 to e to the first, that's just R dot, times theta dot, that's 16 times 1. And when you put that in your calculator, you get around, I'm rounding this quite a bit. It's 260.9. I'll just call this 261 feet per second squared. Yes, sir.
Not that it matters in this case, but is AR, for that equation, is it R, like, the temperature of R minus,
Let's see.
or is it just you do it once?
Oh yeah. I think, yeah, let me get, I wrote it all down in the equation sheet. Let me see here.
But
Yeah, let's see. What did I write before? Yes, you're right. That should be double dot. Thank you. Yeah, please put this rate, double dot right here. Please fix that right there. That should be R double dot, which, like you said, in this case, R dot and R double dot was the same, so it came out right. But yeah, definitely should fix that. Now, this time it asks for the components. We don't have to do the square root since it acts for the actual component. But if it did actually want the magnitude of velocity, you just take same thing as before. This time, when we're doing polar, we do have a VR and a V theta. So you would take VR squared plus V theta squared square root, and then AR squared, A theta squared square root if you wanted the actual velocity, but it just asks for the components. Next, we're going to take a look at this problem, 12-168. For a short time, the bucket of the backhoe traces the path of the cardioid, R equal 25 minus times 1 minus cos theta feet. Determine the magnitude of velocity and acceleration of the bucket when theta is 120 degrees. If the boom is rotating with an angular velocity of 2 radians per second, an angular acceleration of 0.2 radians per second squared at the instance shown. Now, this time, notice that R and theta are not given explicitly as functions of t. So this time we're going to have to do implicit differentiation because R is not a function of t explicitly and theta is not a function of t explicitly. So we're given like R is 25 minus 25 cos theta. So now we know that R is a function of t, and we know that theta is a function of t. So when we take the derivatives of this, we have to do this implicitly. So let's go ahead and do that. So R dot is going to be, of course, this will be 0. And then we went 25 derivatives. So take derivative of the cosine, it becomes a positive sign. But we're going to have to use the chain rule. So we're going to have to do, oh, I messed it up already. 25 sine theta, and then do the chain rule. So we have to take the derivative of this with respect to t. Remember, so we have to do the t dot. Remember, the idea is it's almost as though that we have like a function of t here, but we don't know what it is. We want to take the derivative of it. We don't know what it is. So we have to mark it like as theta dot. Then the second derivative will be the derivative of the first. And then we have to do the chain rule for that. So this is the derivative of the first right here. So we're taking the derivative of this times the second plus the first times the derivative of the second. So we have something like that. See if that'll make sense. And then now for, so for this one now, we're given that it's gonna, we're interested in 120 degrees. And so now you can remember, we're just gonna plug this into the cosine. So as long as you have your calculator set correctly, you don't have this one, you don't have to convert to radians. So but if you're not sure about that, go ahead and convert it and use that. Now we're also given the theta dot is 2 radians per second. And theta double dot we're given is 0.2 radians per second squared. So for that, we're actually given the velocity and acceleration. We don't have to do any derivatives there. So there's a lot of different ways you can handle these. Maybe in this case here, I'm going to maybe evaluate each one of these. So we'll evaluate these at 120 degrees. And so this is going to be R is equal to 25 minus 25 cos 125 degrees. And this is 37.5 feet. Actually, that's a mistake. That should say R equal 25 minus 25 cos 120 degrees, not 125 degrees. Should be cos 120 degrees. The answer is right, 37.5 feet. And R dot is going to be 25 sine 120 degrees. And then theta dot we're given is 2. And that's going to be 43.3 feet per second squared. Our double dot is 25 cos 120. And then this was actually theta dot squared. So I'll just put 2 squared here. Plus 25 sine 120.2. And when you calculate that, that's minus 45.67 feet per second. And actually now you can just plug things into the equation. So VR is R dot is 43.3 feet per second. V theta is R theta dot, which is 37.5 times 2, which is 75 feet per second. AR is R double dot minus R theta dot squared, which is minus 45.67 minus 37.5, 2 squared minus 195.7 feet per second squared. A theta is R theta double dot plus, let me move that up a little bit, plus 2 R dot theta dot 37.5 times 0.2 plus 2 And we have to use that 43.3 times 2 is around 181 feet per second squared. And then finally, if you wanted, the velocity is going to be VR squared plus V theta squared square root. Acceleration would be a R squared, a theta squared square root. And when you put those in, I got like 80, I'm rounding this off, 87 feet per second and 266.4 feet per second squared.